This one is, I will go through some, it's kind of a very quick historical perspective on satellite ocean color radiometry, how it all started and where we are now. And then most of the, probably half or two-thirds of the presentation is on what is a bit new and what is coming in the future. So that's what you have on this slide, lecture content. So well, the first bullet point is a bit of a joke, but ocean color from space, that was not something so obvious to consider at some point. We will go through very basics of ocean color sensors and this quick history of passive ocean color radiometry, and then what's coming in the future and why the new type of missions, new type of instruments have been conceived and for what purpose. So that's a graph I quite often use. It's within second from one of the first of this long series of reports that NASA did as part of the SeaWiFS project. And it's a good illustration, I think, because, what you have here, as you can recognize, and you probably have seen this figure maybe before, two spectra of water-living radiance, one for clear blue waters here, chlorophyll is 0.01 milligram per cubic meter, and this one is for 10 milligram of chlorophyll, so that's typically green waters with much less signal in the blue, increased signal in the green, and here the chlorophyll fluorescence peak. But anyway, then you clearly see the difference. That's the base of ocean color. But as you all know, now if you take the same two situation, but you had the atmosphere on top of it, then you end up with these two curves on the top. And well, as you can see, the difference is start to be quite difficult to see. This is a log scale, so it's emphasizing this the point. But still, that's the situation we have with ocean color radiometry from space. We need to discriminate many levels of signal in a range of in a dynamic range, which is actually quite small. So that's what make it kind of a challenge, and why when it all started, many people thought that would never be possible actually. And how it all started, so these are three figures from the same paper published in 1970 by Clark et al. In Science. And what these people did is, well, they had this feeling that changes in ocean color could be recorded and connected to some of the properties in the water. So what they did, took a plane, put a sensor on it, and made some flights, and they had some measurements in situ at the same time. And they were just, the one on the left is just the total signal that they got at different altitudes. So, 600 feet, 1,000, and up to 10,000. So that was just to show that as you go up in the atmosphere, of course, there is more atmospheric signal, and then you get more signal to record. And then the one in the middle is when they were doing the low flight, sorry. And then they had these three very contrasted situations that they could observe of the percent of, and that's expressed as percent of incident light. So that's not even in any really units, but showing that, the very low chlorophyll situation with the maximum in the blue and so on. So nothing new for you, but, at that time, well, that was kind of interesting to see that, yes, the shape of the reflectance or whatever signal coming back from the water could be interpreted in terms of chlorophyll in that case. And that might seem like, quite basic and crude experiment. But actually, if you read the abstract and the last sentence in that paper, well, they got it all. They had all the challenge and all the things that people have spent decades then to try to solve were already there. And I'm just going to read this abstract. It might not be the full abstract, but an extract anyway. Spectra of sun and sky light backscattered from the sea were obtained from a low-flying aircraft and were compared with measurements of chlorophyll concentration made from shipboard at the same localities and at nearly the same times. Increasing amounts of chlorophyll were found to be associated with a relative decrease in the blue portion of the spectra and an increase in the green. Anomalies in the spectra show that factors other than chlorophyll although affect the water color in some instances. These factors include other biochromes, well, that's sedum, suspended sediment, surface reflection, polarization, and air light. Air light, I'm not too sure, by the way, I should reread this paper, what they meant at that time, but I think that means basically what the atmospheric composition is. And if you go to the end of the paper, there is an interesting sentence that says, if such interference, and that's they mean basically the atmosphere, can be eliminated or identified and allowed for, spectrometric procedures from aircraft and perhaps from satellites, no, that was not even sure, will be of great value in the rapid investigation of oceanic conditions, including conditions important for biological productivity. So, you know, yeah, it's all said there. And that led to the first ocean color satellite sensor. You may know that. Although I'm pretty sure that no one now is really looking at any of this data. They are quite old and not the most exciting, but you know, that's what started this very long time series that we have now. So it was called the Coastal Zone Color Scanner. It was on the Nimbus 7 satellite, launched in October 1978. And here you have the spectral band set. So, you know, a blue, green, greenish, green, red, and near-infrared bands. Okay, that's all we had at that time. And actually, this near-infrared was not really good in terms of signal. So basically, everything that has been done with CCCS was with the 4 visible bands. And well, we just see an illustration of the satellite and the sensor. And well, okay, initial CCCS imagery came, and you know, now we are used to see this every day, and it's absolutely common. And but you know, these first images were kind of a big revelation for the oceanographic community at that time, because you know, there was already some kind of you know, significant knowledge about how the phytoplankton concentrations and the water color was changing in the even at the scale of the global ocean. But that was when you look at the maps that were considered and built at that time from, you know, people had been going at sea, having been at sea for many, many years in different parts of the world. But, you know, they were very broad, long scale distributions. And there was some idea that probably the world was a bit more complex than this, but that's only when this kind of data came that it was fully realized how complex the spatial distribution was and all the scales of variability. So that was, you know, really, we can say, we can use this word, that was really a revolution for oceanography. And yeah, and it worked. It was not just, you know, producing nice images, which is what some other science communities have always tried to tell about ocean color. Well, these people, well, they just make nice painting, but they don't know really what they do. And well, it worked. They had with the CCCS, they had this interesting concept for the validation. They had used a kind of a significant size ship, which was extremely fast. It was equipped with an engine of an incredible power. And the idea was to make a measurement at one point, going very fast to another station and so on. So you could have, in a relatively short amount of time, samples across a satellite swath to do the validation. And they ended up with this, for instance. So that's the log of chlorophyll on the vertical axis and the distance in kilometers along the track. And what they got from CCCS as the dashed line and the continuous line is what they got from the ship. And, you know, as for a first try and the first mission, that was actually quite a good realization. Okay, I'm skipping all the many things happened then in the CCCS time to develop the first algorithms, figure out how to do things properly. But then, even if the CCCS was with very scattered and far from systematic data acquisition, after a number of years, they managed to accumulate all this data and to produce one of the first global ocean color data sets that ever existed, and that was published in EOS in 1989. And that's when people started to see this, that they really realized, oh, okay, now we can really, start to quantify these things at global scale, use this for modeling of primary productivity, and so on. So that was a quick reminder about the very start of the ocean color era. Just a few quick things about, actually what an ocean color sensor does. I guess for most of you, it's quite obvious as well. Maybe not, but for some, maybe not. Okay, well, basically, what do you have to do to deliver some kind of ocean color radiometry observations or imagery? So you need first to collect the light. So that's the first element of any of the sensors. So you need telescopes, some lenses and mirrors to collect the light, focus it to your detector. An important point, by the way, you need to make this insensitive to the polarization state of the light within a few percent. So again, that's all about the design of the sensor. And you may use some coatings on the optics to reduce the generation of unwanted polarizations or to be less sensitive to polarization, use polarization scramblers, which are devices that remove the polarization of the light and so on. Of course, you do this if you do ocean color radiometry. If you don't do this if you want a sensor sensitive to polarization, which is another story. You need to sort this in a number of spectral bands. Then you can do this in a number of ways, but basically, you can use filters. And then you end up with a number of discrete spectral bands. That's what was done on the CCS, for instance. I think, if I'm correct, that's still what was done on CWIFs. Not totally sure, but yeah, I think so. But then otherwise, well, beam splitters, if you want to split the overall spectral range into domains and direct this to two different instruments, sometimes it's needed. And then gratings for if you want to disperse the light and work basically as a spectrometer. Then you are going to convert the collected photons in some electric signal. So that's the same as what Matt showed you yesterday for in situ sensor, but that's the same thing. And again, convert this into some a digital signal, and then sending this to the ground. And that's the transmission capability, which, sometimes it's a very technical thing, but actually it's very important for a mission because that depends on what you are going to be capable of doing with the data. If you collect all sorts of things, but you are not capable of transmitting them fully to the ground, that's not really useful. But then you will need to do the inverse pass, so going from the bits to radians again. So that's all the calibration work. And again, what was described here yesterday for the in situ sensors, that's a bit the same that is done for satellite instruments. Even if generally the effort which is put on the satellite sensors is a bit larger than what it is for, the in situ sensors we use. One of the reasons is, well, okay, once it's up there on orbit, of course, you don't have any way to get back to it and say, oh, by the way, I'm going to recharacterize the stray light or whatever. No, that's done. You have done once, and that's it. So you need to be really, really sure you have done as good as you can before launch. And another important thing is the location of information on the ground. And that's all about the satellite orbit, the attitude and satellite control, determination. So you may have all sorts of device on board your satellite. So you can be sure that you properly locate information on the ground. Okay. So that's a simplified scheme, and that's taken from a report that you can have a look at, the reference in on the slide. That's typically the typical scheme for what we call a scanner. So the coastal zone color scanner was using this principle. Well, I guess I don't need to go into this too much, but that was the CCCS optical layout. That's very often, very quickly that becomes relatively complex as a design. If some of you have been involved in some optical design and have some experience with this, of course, you know what all that means. But basically, again, that's, the way to channel the light to your detector and to make it spectrally sensitive. And this is for MERIS. MERIS was an instrument. It was the first ocean color sensor that Europe sent in orbit in, when was this, by the way? Should know that. 2002, I think. Am I correct, John? Yeah, that's what it is. 2002, yeah. It seems quite recent when you say 2000 something, but actually it's no longer recent. Yeah, so this one, you have this grating, which is the way to disperse light for the spectrometer. Anyway, okay. So what has happened since CCCS was launched? And CCCS is at the, at the very bottom of this slide. Well, quite a lot. As you can see, this is you can find this plot on the IOCCG website, and it's regularly updated with the new missions coming. So in red, they are all the missions that no longer exist. The blue are those who are orbiting at these days, and the gray ones on the top are planned for the coming years. Okay. So yeah, quite a lot has happened since CCCS was launched. One of the important things is actually it's not so clear on this graph, because now there is so much that it's a bit compressed. But the issue we had at that time is that there was a big gap between the end of the CCCS and the start of the next one, which was a global mission, which was SEAWIPS. And when you want to work on long time series, it's never really nice to have a gap like this, because it's making the connection of the two data sets really way more difficult and uncertain. So yeah, a lot has happened. We're not going to go through all this. But basically, well, we'll come back to this, I think, a bit later in that lecture. So let's not. And the last one, as you know, which everybody is very excited at the moment, is the PACE, which has been launched in March this year, which is the first global hyperspectral system. There are a few other hyperspectral sensors on orbit, but they are more focused on the small scale, high spatial resolution observations for land, coastal waters, lakes, and stuff like this. Yeah, there is an interesting book that you can find if you want, and which is a much more detailed and comprehensive history of ocean color missions, but that's a purely NASA perspective. But that's because NASA has launched many of them. That's an interesting book, and that's, it's interesting when you read this to see, how things came up progressively and the rationale for this and all the hurdles that have had to be passed to make this possible. So, all this mission that we saw in the graph before, so in which direction that has been going, okay? Here, this slide is basically trying to summarize the main drivers of the evolution of satellite ocean color, and starting from the lessons learned from the CCCS. So the first thing was, well, radiometric quality. CCCS had a relatively poor radiometric quality. So basically, we want to see more than nuance of blue and green. So we want to get to way more details than this. And for that, you need an increased radiometric sensitivity and quality. So that's the first thing that has motivated the development of these sensors. The second thing, spectral resolution as well. Everyone wants more spectral bands for all sorts of reasons. And so that's why we end up now with these hyperspectral missions being launched, with the hope that this is providing way more information and we can probably do better what we already did, but do more than that. Calibration in terms of, the absolute calibration of the system, but the temporal change of this over the life of the mission. So that's the other lesson learned from the CCCS, because CCCS had only some internal lamps to check the calibration, but that didn't work pretty well. And that's it. There was nothing else. So it was quickly realized that without other device or other programs and way of checking your calibration along the life of the mission, well, you probably cannot do really a very good job. And that's vicarious calibration. I don't know if some of you probably have heard about this, but is needed as well. And that's a lesson from the CCS era as well and the CWIPS era, that whatever you do, even if you do a very good job with your instruments, you have, perfectly calibrated, whatever, you launch everything, you still need to adjust the system it might be it includes residual calibration uncertainties or biases, but it's including as well the unavoidable errors and inaccuracies brought by the atmospheric correction process. And that's something we will see a bit on Monday. And the process to adjust the response of the entire system to correct for possible biases because of calibration and atmospheric correction is called this system vicarious calibration. And that's why space agencies now are really trying to put in place the system that they need to do this properly. The other motivation was to have global data sets. CCCS was a global mission in the sense that it was collecting data all over the world, but it was very patchy, just one image here, one there, so nothing really global. So that was one of the motivations to launch additional systems and to design them differently. And quickly, people started to say, okay, look, that's nice. We have this global view. We know what to do more or less in the open oceans, but we are very interested as well in doing stuff in the coastal waters. And that's, by the way, the irony of the name CCCS, because CCCS was called Coastal Zone Color Scanner, with this a priori understanding that it would work for coastal waters, but maybe not so much in the open ocean. And actually, CCCS revealed the global ocean stuff and was not that good for the coastal waters because of the just having 4 spectral bands. And you can do much, of course, with this. And the other thing was finally, this list of drivers is not comprehensive, but they are the main ones. The last one I have included here is we want to see deeper in the oceans. That has been recurrently, a criticism or something that this community has received. That's very nice, your stuff, but you just look at the surface of the oceans. What's happening deeper is important, so blah, blah, blah. Okay. Well, there are as well at the bottom of the slide other things, of course, which have driven this development of many, many missions around the world. That countries want to demonstrate their capability. They want to have some autonomy in having their own data, and that's completely normal, of course. And well, industry has to get contracts, and the economy has to work. So that's one other driver for developing all that stuff. So to go quickly over these things, radiometric quality. Yeah, I need to go a bit quicker. That's one slide which is summarizing, illustrating rather the evolution of this. So what you have on this graph is what we call the noise equivalent radiance, and as a function of wavelength. And you can see that, well, the larger this noise is, of course, the worse it is. You need to really get this down if you want to have this high radiometric quality and capability to discriminate very low, very small difference in signal. So CCCS was there, relatively high, and then you can see all the other sensors. CWIFS with the triangles is already much better. And in that case, the small cross or for Meris. Okay, so there was a progressive increase in this radiometric quality over time. Now I think it has basically remained at the same sort of levels as what Meris was and what Sentinel or Olchi is now. So that's basically coming to some limit. Spectral resolution. So here you have the spectral bands of many of the past ocean color sensors. So as you can see, there is some commonality, but as well, that's one of the issues we have is every design and agencies are doing their specific things. So, well, generally you always have a band around 443, 45 or something like this, 490, 560. So they are the main, blue-green bands that we need to do ocean color. But then, there are all sorts of specificities. You can notice as well, there is nearly always something at 865 nanometer. That's the atmospheric correction, one of the main atmospheric correction bands. So we will see this on Monday as well. But there was always, and that's one of the things that the IOCCG did, this was to recommend and push space agencies to try to, talk a bit and try to homogenize this kind of thing. So it's easier for the users than to use different data sets. Well, this is another slide which you probably know, and that's to show that now we are in the era of hyperspectral resolution. So we sample the entire spectrum, and hopefully that's going to be a big change. The spatial resolution as well. In that case, there was not a significant change in this. CCCS was at 800 meter. CWIFS 1 kilometer, Meris and MODIS, relatively similar stuff as well. So there is no big change in this because all these missions have a global perspective, want to get to global data sets. And there is no point in, measuring ocean color at 20-meter resolution across the entire oceans. That doesn't make any sense. So this kind of resolution has been more or less the same all that time. The calibration degradation stuff, so that's a very important thing. And that was, again, a lesson from the CCCS because CCCS, there was no onboard way to check this. So only by using in situ data and making all sorts of relatively complicated assumption and things about the data process, about the data quality, could this trend be corrected? So then you don't make misinterpretation of the observation. So that's, you can see this 4 curve for the 4 spectral bands, and they are the degradation coefficient that were derived for CCCS. And there are 2 references here of the two main studies that did this. But then so that was a lesson. Well, that's a problem. That's very difficult to do if you don't have any independent way of doing this. So the situation changed quite a lot for the CWIFs on the left side here, and for another example is for VIRS on the right side. CWIFs is using lunar view, so regularly the sensor is flipped back and looking at the moon, and the moon is a particularly stable target, so you can then check the change of the sensitivity of the response of your instrument. And then you can characterize this over the entire life of the mission, and that's what you have on the left side. And as you can see, at the end of the mission, the band 8 was 20%. The degradation of band 8 was 20%, so that's quite significant. And even the 2-3% degradation only of the blue bands are still quite significant. And if you don't properly correct for that, you cannot use the data to do anything. You're just completely wrong. And as you can see on the right side, for VIRS, the numbers are even much larger. And so the first VIRS on the SNPP suffered a very quick change of sensitivity. As you can see, the black curve, for instance, for the band number 1 is just dropping by 30% in just 2 years. So, well, again, that's just another example for the Meris mission. So that in that case, that's a different technique. There is no view on the moon. There are diffusers on board the satellites, and these diffusers are used to basically look at the sun and use this to track the change of sensitivity of the instrument. And one of these diffusers is used, I think, at nearly every orbit to calibrate the data, and the other one is used way less frequently. It's kept, protected from any degradation and used to check the system. And you end up with this curve as well. As you can see, this instrument is way more stable in time than the others. After 50,000 orbits, the worst degradation was 5% for this band, number 8, which is probably one of the near-infrared bands. Okay. Yeah, so system vicarious calibration, like I said, it's quite an important, it's actually a crucial part of the ocean color radiometry from space activity. So it's all about the requirement, okay? Because yeah, one thing which is important, by the way, whatever sensor you develop and you want to send in space, or sensor you want to use in the field or anything like this, to develop these sensors, to decide which technology you are going to use, which design, and so on. Well, you need first to tell what you are going to do with this, and what sort of uncertainty or errors you are going to accept or not. Doesn't matter to develop a very highly sophisticated sensor if you just want to do relatively, crude, basic discrimination between clear and turbid waters, for instance. Okay, so the first question is, which errors can we tolerate on reflectances in the blue and green that we still can derive chlorophyll within maybe, say, plus or minus 30%? This is the requirement. And this is from what you start to then progressively come up to the characteristics of the instrument you need to respect this requirement. And basically, the answer was, from many studies, that we need something like a 5% uncertainty for the blue bands over oligotrophic waters. And oligotrophic waters are where the signal in the blue is the largest. Okay, that's one requirement, and it has driven a lot of the development of the sensors we have seen before. And it was relatively quickly realized that this requirement could actually not be met with only pre-launch and onboard calibration capabilities only. Okay, because 5% on LW at the sea level, because this signal is at the best 10% of the total signal you get at the top of the atmosphere, it means that you need a 0.5% uncertainty or accuracy at the top of the atmosphere. And no one is capable of doing this on a lab. The best laboratory calibrations, radiometric absolute calibration characterization will have an uncertainty of 1 to 2% probably, okay? 0.5, no way. So there was the need for a process by which overall we eliminate the biases in ocean color products. Yeah, it's all about biases. The uncertainty in this, the scatter of data are not really considered here. It's all about, on average, removing the bias that may still exist in the overall observations. And basically, to do this, you have to measure LW as accurately as possible from some in situ system, and you probably know the MOBI buoy in Hawaii, which is doing this. Add the atmospheric signal in some way. So you get the total, you can model the total signal that the satellite should observe, and you compare to what the satellite actually observed. And you make the ratio of the two, and you get, again, the calibration gain. And you do it again and again and again on as many match-up points as you can. You average this, and you get your system vicarious calibration gains. Yes, beware of one thing. This is only used to adjust, let's say, the starting point of your ocean color time series for the mission. It doesn't do anything to check the temporal stability of the mission. That's done independently using the lunar calibration on the onboard diffusers, whatever the mission has been designed to do. SVC is only to adjust basically the starting point and removing the bias. The need for global data sets. So yeah, that's basically illustration of all these things I listed in the slide before. This is typically a day of CZCS sampling, okay? That's a global view. I should have added maybe the coastline, so that would be a bit clearer, but this is one day of global observation from CZCS, okay? Just a few images here and there. Just because there was no capability to store more data and to send more data on the ground. As well, because it was not the objective to do anything global with CZCS initially. This is what you get from CWIFs. That's already much better. And with some other sensors like VIRS, you can do it even better. Okay, so if you have systematic observation and you have a relatively large swath, in one day, you get already quite a significant coverage. And of course, you can now, that's what many programs do, you can use CWIS, MODIS, MERIS, everything, and try to merge them all to get to this multi-mission data sets, which have basically, some of them have basically a full daily coverage. Well, in some part of the ocean, there are a lot of clouds, so sometimes you need definitely more than a day to get something, even if you have many sensors coming across, but still. Here I have put basically the three sources that exist at the moment for this kind of global mission data sets. And again, probably many of you know that. So the ESA Ocean Color Climate Change Initiative, the Globe Color data set, and then the NASA OBPG data set. The first two are definitely multi-mission merged data sets. The OBPG, they don't provide merged data sets. You can find, MODIS and MERIS and CWIFs and whatever, but they don't do the merging thing. Okay, so that was quite kind of a quick, well, not so quick actually, summary of what has happened in the past, the rationale for what has driven all the evolution and the development of the new sensor. So now let's have a look to what's coming up for the future. Well, the first thing is we definitely want to still do a bit more of the same. And sometimes that's considered, if you submit a research proposal to your funding agency and I'm going to do a bit more of the same, well, you're not many chance to get any funding. But that's actually a very important thing to do because these missions have one particular mission, is to keep this global observation of the oceans repeatedly over years and years and years. So we can build this long-term, what we call climate quality data records, and we can hope to identify the long-term changes from which may be driven by climate change, to speak quickly. And as you know, the phytoplankton in the oceans is something which is varying at all sorts of temporal and spatial scales. It's a highly dynamic signal with variability on the daily scale, on the seasonal scale, on an interannual scale. So finding maybe some relatively small long-term trends and changes in a data set like this really requires to have this long-term record. We're getting there, we are nearly at 30 years now of data. And but that's what, and I guess the situation is quite good in this respect because most space agencies have got the message and they know that's one of the things they should do is to try to build this consistent long-term data record. And yeah, and this slide is just extracted from a paper published in 2010. where some, so that's from a modeling group. They were trying to look exactly at, how long this time series of ocean color should be. So then we can start to really identify, separate the interannual variability from the long-term trends. So, and their conclusion basically, sorry, was that, I think it's on the slide, it should be on the slide, but anyway, that's probably, at that time, they said we need 40 years of continuous stable observation to be able to do this. And yeah, their conclusion were, detection of climate change-driven trends in the satellite dataset is confounded by the relatively short time series and the large interannual and decadal variability. So recent observed changes in chlorophyll, primary production, and so on cannot be unequivocally attributed to the impact of global climate change. We said this in 2010, but we can still probably say it in 2024. It's still unclear, well, maybe the answer is actually that there is no impact, and actually phytoplankton is resilient and dynamic enough to be able to cope with all sorts of conditions in terms of temperature, nutrients, whatever. We will see. We still don't really know. Yeah, and that's the next point. Analysis of model chlorophyll and primary production from, they did a 100-year run, suggests that on average, the climate change-driven trend will not be unambiguously separable from decadal variability until 2055, and that was written in 2010. So that's where this 40-year time frame comes from. And the graph on the left are the illustrations taken from their work, and where you can see the different curves showing how things are evolving under different scenario, and that's indeed you need these long time scales to separate the signals. Maybe, yeah, I can keep this one as well. The other thing is, and that was said in this slide as well, in the first bullet point here, they say the relatively short time series and the large interannual and decadal variability. And that's something we showed quite clearly in a paper we published in 2009 with Elodie Martinez, who was a postdoc with me at that time. And that's where we basically, well, I will tell you about the figure just a bit later, but basically what we showed was that there was this, what we call decadal oscillations of the system at the global scale, where, for more or less a decade, the system, the connection between physics and phytoplankton is going in some direction, but maybe this is going to be going in completely the other way for another decade and so on. So that's making very complicated, very difficult to interpret the change you have on a relatively short time scale. And that's all came because there was a paper published in 2006 by Mike Berenfeld in Nature. So that's the plot on the very bottom here, where basically, and what you have on this map with the yellow, blue, deep blue, light blue, and purple are basically areas where either the chlorophyll and temperature are going or increasing at the same time, or both decreasing, or both going in the opposite way. Okay. And as you can see, this is distributed as large entities across the entire world ocean. But this study was based on seaweeds, and at that time they had, I think, 10 or something like, not even 10 years actually, because it was 2006. And seaweeds was launched in, if I'm correct. Anyway, that was a relatively short amount of time. And they ended up with this. And their main conclusion was that, the impact of climate change was basically to get to a more stratified ocean. So there is less influx of nutrients from the deep, basically, and then the chlorophyll is decreasing. And they showed this relatively nice connection between the two. And they attributed this to probably the effect of long-term climate change. But then we redid exactly the same study, basically, but then we used the CCCS and the SeaWiFS dataset, we managed to connect them, and then we had a much longer record. And then we ended up with the plot, the second from the bottom, so the number C, panel C. And we did the same analysis where the things are going the same way or in the opposite way, and we ended up with this map. And as you can see, that's nearly the mirror map of the one that Mike derived at that time. And our interpretation of this was exactly because of these decadal oscillations of the system, going in some direction for some time, but then going in the opposite direction in another decade. So what does this mean is then you need quite a number of decades to see how this system is oscillating and changing, and maybe then having the possibility to derive the long-term trend or changes. And while I'm not going to describe the details of the plot on the right, but basically what this plot shows is that this is connected to this, global climate indices like the PDO, which is the Pacific Decadal Oscillations, or the AMO, which is the Atlantic something oscillation. The M, I have to say anyway. And these indices are basically built from a number of parameters of the physical environment, like the wind, the difference in pressure, temperature, and so on. Okay. Well, that was just to emphasize that, yeah, there is definitely this need for long-term data sets. So space agencies, please continue to do this and don't do crazy things that would completely disrupt the time series. Okay, another thing which is, well, not only the future actually, because it has already started, but that's probably going to grow significantly in the next 10 years, are having ocean color sensors on the satellite on geostationary orbits. Again, that's something that we started to push this idea maybe 20 years ago or something like this. And again, at that time, most of the people were saying, well, there is no way you cannot do ocean color from so far, because as you probably know, geostationary sensors are basically 36,000 kilometers from the Earth. And in terms of signal and everything, many people were not convinced at all that this could work. Anyway, and why doing this? It's because, first bullet point on this slide, current missions have one major drawback. They observe the ocean at best once a day and always at the same time. Okay. Kind of thing in terms of sampling, a very dynamic environment, that's not very good. So the resulting repeat is at best of a few days, and exceptionally less. But many processes in the oceans, whether it's coastal ocean or even the open oceans, occur at temporal scales which are largely inferior to the day. So, and when you want to obtain a full spatial coverage of a given area, you need to accumulate data over a long period of time when you do this from orbiting systems. So that's blurring, smoothing, whatever you want to call it, the spatial temporal variability. So there is an obvious mismatch between how the oceans vary and how we observe them from space. And that's not only ocean color. I mean, every, looking at temperature or other things, it's the same issue we have. So that's where the idea came from, to have this sensor on the geo orbits. The advantage of this is, first, when the conditions are really good in terms of solar angles, view angle, cloudiness, and everything, you can access to the diurnal dynamics of the ocean. That's a very interesting thing to do, because there is definitely a diurnal variability in the oceans, wherever you are. So the first objective in this case is to, really understand and study the ocean ecosystem at the diurnal scale. So that's because of the cycle of photosynthesis and respiration, which are generating a diurnal variability in the particulate pool. So if you generate variability in the particulate pool, you are going to generate the variability in the inherent optical properties and in the reflectance. Well, the second point, because you sometimes you're not able to do this even from a geostationary orbit. You might have too many clouds, or maybe you try to look at an area where the view angle is a bit too large, so the uncertainty in your correction is going to be high, so the dial signal is going to be completely destroyed. But still, so you may have fewer observations over a day, but still you can relatively quickly, you can work and understand rapidly evolving phenomena, which are, varying at the scale of at the daily scale, maybe. And that's, I have listed here a few, like, river outflows, aerosol plumes, phytoplankton blooms, mesoscale or sub-mesoscale features, and so on. So this is not necessarily linked to the biological functioning of the ocean. It's rather often under the influence of physical forcing, but then you can really follow these things happening much better than with orbiting sensors. And then, well, there might still be conditions where you cannot really do this, but still, with these repeated observations every day of the entire globe, you can much quicker get to a full image. So, this blurring of the spatiotemporal variability that we have when we accumulate too many observations from an orbiting system, you won't have this. So you still can, dramatically improve coverage with at least one observation of good quality per day in many places. And this is, for any operational use, from, data simulation in models, and to providing services to all sorts of, activities. That's much better if you can tell people, look, I can guarantee you that you will have an observation every day. Then, well, maybe once a week if everything is good. And okay, just to illustrate this, well, you probably have seen a few things like this, but yes, there is indeed the diurnal variability in the ocean. That's what is illustrated with the on the top left on this slide. In this one, it's a plot of the particulate beam attenuation coefficient, so CP, as a function of time of the day. So that's the curve which is, here, okay, showing, a clear increase along the day. Well, that's basically, photosynthesis, creating more material, cells subdividing, growing, and then CP increasing. Then, whoops, it starts to re-decrease. That's all the respiration process. Particles will settle in the deep. So a change, so that's basically the change of the particle population in the upper layer. And the other curve is basically the derivative of this one. So that's the rate of change of the CP. But again, that's CP. CP is, as you know, absorption and scattering. That's not the reflectance, but there is definitely a diurnal variability of the reflectance because of this. And one of the ideas behind this is if you can quantify the amplitude of this diurnal variability, that tells you something about the productivity of the ecosystem. So that's something we did, for example, and that's the plot on the bottom right, but from in situ data, I have to say, not from any satellite stuff, but that's again from the Boussole time series. So we basically look at this, at this diurnal amplitude of the CP, connecting it to the variability of the particulate organic carbon and deriving some productivity from this. And that's the black curve you have on this plot with the 2-year time series. And the gray dots behind this are the productivity we could derive from the classical chlorophyll-based model, and the agreement is quite good. So you can imagine if you manage to do this from a geo platform, you can quantify this variability over the day. So you have a direct estimate of primary productivity without having to do too many assumptions using models and stuff. It's nearly a direct measure of productivity. Well, other advantage of the geo orbit, I said, looking at dynamic events. So that's just an illustration from the GOSI sensor, which is above the Korean Peninsula. And let's play it again. Whoops. You can see these plumes of sediments moving over the day. And I think the observation that they have is once every hour. So that's really a key thing. It's very important as well in all this coastal environment where there is a significant tidal variability as well, because again, an orbiting sensor is going to come at different time of the tidal cycle, because it's coming always at the same time of the day. One day it might be low tide, and the next day it's going to be different, and maybe 10 days later that's going to be high tide. And when you connect all these observations, they correspond to different phase of the tidal cycle. So that's a bit confusing your interpretation. And this one is to illustrate this gain in terms of how many observations you get on a given area. So, on the left, it's typically what you would get with the constellation of the two Sentinel at the moment, Sentinel-3A and B. And the color here is just the percentage of coverage you have. And I think it's just for a day. March. No, sorry, it's for 1 month for March. So, some areas are nearly covered 100% during the month, some less. And on the right side, you have what you would get from a geosensor. Okay, so you clearly see again, you can observe way more of the oceans. There are some challenges, of course, behind this. Oh gosh. You are far from the Earth, so if you want to get to the same spatial resolution, you would need to really increase a lot the sensitivity of your instrument. So it's all coming back to this issue of signal to noise. But because on a geo orbit, you are fixed, you move at the same time as the Earth, so you can stare at a given area for relatively long, so you can increase significantly the integration time, and then you can get finally to the signal to noise ratio very similar to the one you have with an orbiting sensor. The pointing stability is a challenge. You're very far, so the extremely small change and vibration, and so end up with large change of what you are looking at on the ground. So that's a challenge. But all these challenges have been overcome, in studies and with the two GOSI now in orbit and demonstrating the feasibility. There was an IOCCG report on this. Well, it's 2012, so that's already 12 years ago, but it's basically still a good summary of all this geo advantage and challenges. Do we have plans? Yes, of course, there are more than plans. There are already two sensors like this on orbit. What's coming, maybe still a few years to go. This is still in planning. The instrument is being built. That's the Glimmer. So geosynchronous littoral imaging and monitoring radiometer. So that's a US-led mission. So I think we're still at least 2 years or 3 years before this system is in space. This one is not about looking at the entire Earth's disk. It's going to look at specific areas and this yellow squares you have on this plot. I think the plot is it's slightly outdated, so I think now it's even more concentrated on the Gulf of Mexico. Okay, and unfortunately, I don't have any more slides actually do we have plans? There are some plans in Europe and others in the US for more ocean color from the geo orbit, but they are in the very infancy, and I don't know, maybe in Europe it's going to take still another 10 years before we see anything like this. Okay, well, the first thing, going hyperspectral, that's what the future is made of course. I just wanted to remind a quick things about this hyperspectral observation. So that means continuous with quote observation from the near UV to the near infrared at high spectral resolution. But you have to keep in mind that what we call spectral resolution is, as illustrated by this very kind of naive sketching, but is the distance between the central wavelengths of successive bands in the system. But each of these bands has a spectral response function, which is illustrated by this Gaussian curve here. And what we call spectral sampling is actually the width of this function. And you might have a sensor which has a quite narrow spectral sampling. So you might expect that then you're going to be able to really see small spectral change. But if this function is relatively wide, it's averaging, the signal over maybe 10 nanometer. So then there is already some smoothing of the signal because of this. Okay. So there are the two main characteristics of an hyperspectral system, and that's depending on the technology which is used, of course. The basic assumption here is we can derive more information on ocean ecosystems from using a richer spectral information as compared to the few spectral bands we have on the most of the sensors. Okay. Yeah, well, just a point in that last bullet is actually the MERIS instrument and the OLCI instrument are already hyperspectral systems. They are spectrometers. It just happened that the decision was made not to transmit all the data to ground, but just to sample some spectral bands. But in theory, you could use OLCI to do what space is going to do. It's an hyperspectral sensor as well. Yeah, and some of the applications. So the first point here is saying going hyperspectral is an attempt to solve ill-posed problems by bringing more independent observation in the system. When we do, we apply this inversion algorithm to ocean color, this semi-empirical, semi-analytical, whatever you call them, algorithms, there is always very often situations where you have more unknown than you have independent observation. So, well, you end up in this situation of having a ill-posed problem. So the idea is maybe we won't be so often in this situation if we have more independent observation. Now there is a debate in the community, and there are a few papers that have been published about this, about, well, at the end, how many independent observation we have. It's not like this, I don't know, so 700 divided by 3, 250 maybe observation or all independent observation. They are not, of course. So that's the next few years will tell us definitely what we can do with this. And I have listed, a number of this problem that we have a hard time to solve properly now, and that might be helped with hyperspectral observation, like bathymetry in shallow and clear waters, of course, phytoplankton functional types, harmful algae blooms, and so on. And the little plot on the bottom, which is the phytoplankton absorption spectrum, and the first derivative of this is typically the sort of analysis you can try on hyperspectral data to, and if you have the independent observation on phytoplankton groups, that's a way to identify them. I'm going a bit quicker because of the time. Oh, that should be okay, actually.
Thank you. I just wanted to point out that, yeah, it's about time. Thank you.
Okay, sure. Yeah, okay. So the main thing which is attracting attention at the moment is space. So plankton, aerosol, cloud, and ocean ecosystem. So that's the website. I just wanted to show you one, it's a very basic little thing we did with a student a few weeks ago. Going to start to have a look, comparing pace with what we're slightly more used to, the Sentinel-3 OLCI. So I told the student, just take an image. Well, find a day where you have, Olchi and Pace looking at the same area. That's Western Australia here that you can see. And just make some, just have a look to compare the remote sensing reflectance spectra from the two. And she selected a number of this location with the small pins that you can see a bit everywhere here. And, in very coastal areas, offshore, try to sample quite a number of different situations there. And then you have an example of a few of these comparisons on the right side, on the top. So the black dots are, of course, the spectral bands of Olchi. And the continuous red curve is what Pace is providing. And well, surprisingly, actually, if you look at the panel A and B, well, that's the left, the ACE panels and B, D, F are the same, but on the right side, it's on the log scale. So we can have a look to the small variability in the red bands. And we were a bit surprised because actually, typically the top comparison is quite good. But it's actually coming from a pin which is in a very shallow, turbid kind of environment. So we were expecting maybe that's where the difference would be significant. And actually, at least so far, it's very good. And actually, the one on the bottom, so the E, is an offshore pin 22, which is, where is it? Somewhere there. And then you can see that starting from 500 something, well, in the blue, there is a big discrepancy now. And we just don't know what's happening with space, but it's plateauing. And but okay, there is no vicarious calibration applied for the moment. They are still, trying to figure out everything. So I'm pretty sure that when they will have introduced the SVC, corrected probably for all sort of things in their processing, this situation will improve definitely. But the other thing I wanted to illustrate here is, you can see in the red curve here on this plot, here, there is this relatively small variability, small spectral variability. That's not what you would expect in a remote sensing reflectance spectrum. Normally that's a reflectance, so it should be smooth. There is nothing in the IOPs, at least as far as we know, and the spectrum of the IOPs, backscattering, absorption, whatever, which has a very high, significant spectral variability like this. It doesn't exist. So normally you should not see this in the reflectance. The small scale variability comes from the solar spectrum, but this is because you normalize LW and ES, that should cancel out. And your remote sensing reflectance spectra should always be quite smooth. So that's not what we see here. So they probably have, still a bit of work to do on processing and so on. Anyway, and well, the scatter plot at the bottom is just, putting all this data together and looking overall at the match between the two. I think that's actually a very encouraging result for the PACE mission. And I'm pretty sure, when the SVC would have been included, there will be quite even a better agreement than this. Okay. Yeah, that's okay. I thought I was late, but not too bad. Other things which are coming, but it's not really completely the future. It's already happening now. And it has happened a bit in the past, but not that much. There are ocean color sensors recording the polarization state. And, I told you at the beginning, normally, generally, ocean color sensors don't have to be sensitive to polarization, but on the opposite, you might want to do specific instrument for this. And basically, again, the idea is to introduce an additional independent piece of information in the inversion problem. So the polarization state. Polarization is highly dependent on the particle composition, so the index of refraction, and the particle size distribution as well, and the particle shape as well, so many things. So the main aims of this are, one, to maybe better identify the aerosol in the atmosphere, to help maybe do a better atmospheric correction. And the second point is to discriminate between mineral and biogenic particles in the oceans. There are two main objectives. Well, there are others, but there are two main objectives of having these polarimeters on board as well. And the plots here are taken from a paper by Loisel et al. In 2008. So the one on the left is the polarization, degree of polarization. And the two curves are for different refractive indices and the same particle size distribution. So you can see that there was a big change in where the maximum of polarization happens. And the same thing on the right, but for a different slope of the particle size distribution. So and again, you see the big difference. And that was done in the past. There was this polder sensors that CNES launched in the 1990s and up to, not sure when the last one, by the way, died. And the MISER from NASA was as well equipped with polarimeter. And on the left side, you have some illustration of, again, from the same paper, I think, from Loisel, in two different parts of the world, of the remote sensing reflectance on the top and the degree of polarization on the bottom, and clearly showing the variability of this and how you could use this maybe to map this biogenic versus mineral particles. At this time, there are two, as far as I know, two missions that have polarimeters on board. So the SGLI from JAXA, and on board PACE, there are actually two polarimeters. And in the near future, EUMETSAT is going to launch the new generation of the, what's the name? A new generation of orbiting satellites, and they will have this 3MI polarimeter on board. So it's not a huge number of missions, but this is definitely coming, and this is definitely, this is where there is quite a lot of fundamental work to do as well, because it's still really hard actually to properly interpret these polarization measurements. They depend on so many things, and it's quite, and that might explain, by the way, why it has been relatively slow to see this instrument coming in the community. Well, the atmospheric community are much more used to this than we are. Yeah, and they saw, well, that's just for reference, the two polarimeters that are on board the PACE missions, collecting data at the same time on the OCR hyperspectral radiometer. Another thing which is coming, okay, of satellite-borne LiDARs. And here the justification is, if you remember, the drivers for the evolution is we want to see deeper. So that's what it is with the LiDARs. So passive ocean color allows accessing a signal whose 90% come from depths, roughly speaking, equal to 1/kd. And in the clearest water, this is about 20 meters in the blue. And otherwise, it's going to be much less than that. We know, however, that the vertical structure in the upper layers is important as well. It's not necessarily uniform. So hence this idea that LiDARs could help because they are precisely designed to resolve vertical structure. So far, LiDARs on satellites have been essentially used for atmospheric purposes. And ocean LiDARs have been rather deployed from ships or aircraft with all sorts of applications, but most often that was to determine the bathymetry, not really to look at any vertical structure in the water column or anything like this. So satellite-borne LiDARs, you can look at this reference here. There is a lot of interesting information in there. Well, very quickly, the principle of this is, you send a signal and you have a receiver which is working at a very, very high frequency, and then you can profile because you get the signal coming back from different part of the medium you are looking at. The difficulty we have in that case is generally LiDARs were used for the atmosphere. If you want to use them for the oceans, but you still have the atmosphere, of course, in between, you have the interface, and then the water. So that's complicating the problem a bit in terms of interpreting all the signal. But that works. This is an example with the HSRL LiDAR. I'm sorry, I have just a blank trying to remind whether that was done from a plane or a satellite. I think it's airborne, but in any way, they managed to get, you know, a profile of the particulate backscattering coefficient, a function of depth. So in situ measurement in black, and what they got from the LiDAR in red. And as you can see, they managed to get this over the first 2 optical depths, which is quite a significant achievement. And on the right side, it's just a scatter plot of this data. So there is definitely hope to, you know, to do something significant with this. The other advantage is LiDAR. Yep, sorry. Yep. Yeah. Oh. Yep. Oh no, because in that case we look at the radiance. So there is not this law. This law would be it's when the distance from the sun to the source to the ocean would change, and that's what we have to take into account when we take into account the eccentricity of the Earth's orbit, but not. Yep. Yep. Yeah, there is attenuation in the atmosphere. Yes. Yeah. Yeah. No, it would decrease as function of the attenuation coefficient in the air. So it's not. Yeah. 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 Mm. It should be, but you know, correct that the intensity of the signal, which is decreasing along its way back to the sensor, will probably mean that, you know, in terms of how much energy they have to send with the signal has to be quite significant. But yeah, I think because they made some demonstration as well with the Calypso LiDAR, and it's definitely a spaceborne, and that was working as well quite. No, the thing I'm still struggling with this, I can tell you, is, you know, photons who go deeper than the first penetration depths the understanding is they have little chance to escape anyway. So, and I have been discussing this with people doing the LiDAR, and they never gave me, I think, a very satisfying answer to this. How this work? How can they pretend to see that deep when actually, you know, photons having reached this kind of depths have very little chance of getting out of the water? So I'm still a bit, I know, yeah, yeah, I know, but it's not 90%. So yeah, I'm still a bit, yeah, yeah. Mm. It is, but that I guess, yeah, that's probably, you know, the way the LiDAR works is, yeah, it might be a bit tricky to understand sometimes properly. So there are definitely things to dig in a bit deeper with this. The other advantage is they work night and day because it's an active system. You don't rely on the sun as a source. And then for the polar area, that's kind of an interesting capability. So Mike Berenfeld published a paper in 2017 like this, where they had a look to, you know, what sort of coverage they can get on the polar areas and then have the capability to follow what's happening, not only when there is sunlight there, but over the entire cycle. Well, not going into the details of the figure. One thing, however, and maybe, no, it's not on this slide. One thing not to forget, however, is the LiDAR is giving you a long track observation, of course. You don't have a wide swath of observation. So that's one of the weak points of this. You get a line of data, and you have to accumulate also quite a bit of this to get some. It's just the same issue that they have with the altimeters, well, before the SWOT mission came, but altimeters are giving you a long track data as well, and then you have to interpolate in some way to get some full coverage. Again, high spatial resolution sensors. Well, that's as well a bit of the present, of course, but that's developing, and there are more and more of this which is used. As I reminded before, most of the sensors we use, they are moderate spatial resolutions, 500 meter, kilometer, 250, whatever. And that's totally fine for most of regional, global applications and so on, but not necessarily well adapted to more local phenomena, in particular in coastal environments. So there was, this interest for high resolution sensors has really developed a lot. The problem is most of the sensors we use in that case are not actually designed originally to look at water targets. They have been mostly designed for land applications. So there is a bit of work to be sure that what we do with them is proper. So that's an example of and of course, when you look at this kind of image, that's a Sentinel-2 MSI, that's amazing. You see all that stuff and you get very excited and, but of course, this is just what we see with our eyes. That's the combination of a few bands to get this nearly true color observations. But then, of course, what we have been doing in this community for years is just to try to get to quantify things, not just to map stuff in a qualitative way. So you have to question that, okay, can we do this with sensors? And there's, of course, a bit of an issue. So when you go to higher spatial resolution, you generally go to lower signal to noise, okay? Except if you would develop, kind of extremely sensitive and huge and very expensive sensor. But generally, if you look at a smaller part of your target, your signal to noise is going to decrease. So is it still acceptable and good enough for ocean applications? And when is it that the radiometric quality is becoming so much degraded that the quantitative aspect of satellite ocean color is basically lost? Another thing which is really complicated actually is, remember, I think it was in John's lecture yesterday. Okay. But there was this Cox and Munk model we use for the modeling the distribution of the wave facet and their impact on the signal and so on. That's okay when you look at you use relatively moderate resolutions, spatial resolution, because your pixel is including all this wave in all sort of direction and so on. It's no longer true when you look at a 10 meter or 20 meter scale. So that's becoming quite difficult. The above may sometimes be an advantage. I don't know why I have put this here. Shadows, yeah. Shadows is generally something we don't consider when we work at relatively moderate spatial scales, but when you start to look at very small scale, that may become a problem. So, and yes, and because most of the use of this high spatial resolution observation are for coastal areas, you put yourself in a situation where you have less spectral bands, you may have less signal quality, but then you have a more complex atmosphere to deal with. So that's making things quite hard. Maybe I can skip this if you will address this in detail, John, but typically this is an image of the ocean with all the little waves and so on. It's at 1 kilometer basically resolution. So, and the equation on the bottom are this Cox and Munk model, which is telling you about the statistical distribution of this and how you can model the reflectance of this. But the small naive drawing I made on the right side is to illustrate that when you go to this very high spatial resolution, maybe here you look at the wave facet, which is like this. Here you look at that. There is no, this statistical distribution no longer works, so you have to do something else. Yeah, but that's another example of observations from this kind of sensor. That's Landsat 8 on the left, again Sentinel on the right, and here actually it's the image is taken above one of these wind farm in the North Sea. You can see all the small dots, and you can see the wake of this that they left in the ocean. And that's probably the turbidity. There was current coming. There was a big structure in the water that's changing the flow, and you can see this in this image. And that's the same on the right side, I think. Sediment plumes in the North Sea. Yeah, that's the same. Well, this one is just an illustration as well, because indeed, and that's always that has been I think most of the motivation to use this sensor have come from this kind of images where people realize how much they could get from that. But again, to go from that to quantities, it's a bit difficult. It's nearly, yeah, I need to conclude soon. But just an example of something we did just 2 years ago, using Sentinel-2 in some very coastal area of Western Australia, as it is illustrated on the left, and using Sentinel-2 and 3, trying to merge the two to take advantage of the spectral resolution of Sentinel-3 and the spatial resolution of Sentinel-2, and then looking at whether we were doing not too bad of a job with the reflectance. And that was quite okay, because we had in situ systems to validate what we were doing. And you have this scatter plot here for Sentinel-2, and the one on the right is for Sentinel-3. And we are quite satisfied with this, actually. Okay, to conclude, another thing which is definitely coming at the moment are all these CubeSats. And here the motivation is generally completely different, is to say, look, can we do things quicker, cheaper? Can we use this to test all sorts of different technologies before maybe we move to the bigger missions? It's very much used as well in universities to train students to build something and have an hands-on experience and to launch something in space. So there is a lot happening there. And even if, again, it's always the same story with new things coming. Some are a bit skeptical, but there is actually a lot you can do from this, even this small thing. It's not necessarily the one unit CubeSat 10 by 10 by 10. Sometimes you need 2 or 3 or maybe 6 of them, but it still remains a very small thing to do, and the cost, and so that's exploding a bit everywhere. And that's just here an example of an IPEX spectral camera, which is supposed to fly on an ESA CubeSat. The Seahawk is a good example of that. They were just trying to replicate the SeaWiF's capability on a CubeSat. It's a 3-unit CubeSat called Seahawk. And you can get to this and have a look at all this image on the Ocean Color website as well. Well, that's just a bit of publicity for my university, because there is a group there which is developing a new platform as well, new CubeSat platform, which is even more compressed than everything else. And then that leaves a bit more space for the payload, and they are trying to do all sorts of different applications with this. And CSIRO in Australia is as well working as part of what they call the Aqua Watch program, to try to have sensors capable of identifying cyanobacteria in lakes and rivers and stuff. And they have developed something which apparently is quite convincing. They have tested it from a drone. So again, there are plenty of these CubeSat thing happening in the world, and that's definitely one of the future.